Good afternoon, ma'am.
Switch on your camera, please. Sound propagation. So first of all, I received homework only from Dhyan. What about others?
Ma'am, some of my ray diagrams are left. I will just complete them and send you.
Ayan,
Ma'am, I will send.
when? When will you send? So if I don't get it today by 4 o'clock. 4 o'clock, let's keep it today by at least 7 o'clock. If I don't get it today by 7 o'clock, then I will not take any more classes, okay? I'll take only for those who have given me the homework. So today by 7 o'clock, you have to submit. Otherwise, please don't join. Okay? Yes or no?
Yes, ma'am.
Ayan. Ayan, I didn't hear from you.
Yes, ma'am.
Okay. So propagation of sound waves. So we have two parts in this chapter. Part A, production and propagation of sound waves, and the part B, that is the that we have for the infrasonic and ultrasonic sound. Okay, infrasonic, sonic, and ultrasonic sound. So first we'll be doing part A. This is a very simple chapter, and you know most of this because we have done in class 8 also. First of all, what is sound? What is sound? Please be interactive, switch on your camera and keep answering.
Ma'am, may I say?
Yes, Ashi.
Sound is the form of energy through which we hear things. The vibrations which are made through the environment, we name it as sound, basically.
Yes. So sound is a form of energy. Sound is a form of energy. And what does it do? It produces the sensation of hearing in our ears. It produces a sensation of hearing in our ears. So sound waves are mechanical waves. What do you mean by mechanical waves? Any idea what do you mean by mechanical waves?
Ma'am, the waves which are formed by machines, but the
No.
energy.
Ma'am, can I?
Yeah.
Ma'am, the sound which is produced by mechanical energy.
Yes. Because they are produced by vibration, in which the potential energy gets converted into kinetic, kinetic gets converted back into potential. So it is formed because of the mechanical energy. All the vibrating bodies, they produce sound waves. All vibrating bodies produce sound waves, and all the bodies, they have certain frequency. They have certain frequency of vibration. But it's not necessary that we will be able to perceive those vibrations, because our ears have a limit. What is the limit of hearing for our sound? Hearing limit for our ears. Which sound range can we hear?
20,000 hertz.
From that's the upper limit. 20,000 hertz is the upper limit. What's the lower limit?
20.
20 hertz.
20.
Yes, so our ears have a limitation. We can hear sound waves which are from 20 hertz to 20,000 hertz. Okay, if we don't have that much, if the frequency of the sound wave is more than 20,000 hertz or less than 20 hertz, we cannot hear. So those sound waves which are below 20 hertz are known as? Any idea?
Ultrasonic.
No. Below 20 hertz?
No, ma'am.
Infrasonic.
Infrasonic, yes. Infrasonic. And those which are above 20,000 hertz are ultrasonic. Okay. So, sound is produced when the body vibrates. All the vibrating bodies produce sound. All the vibrating bodies produce sound, but we cannot hear sound because the waves which are below 20 hertz, we are not able to hear, and waves which are above 20,000 hertz, we are not able to hear. Okay.
Yes, ma'am.
So when we hit the drum, the membrane of the drum vibrates and vibrating body produce sound. Similarly, we play guitar, we strike on the strings and the strings start vibrating. Then we have an air box below it, and that air in the air box starts vibrating and loud sound is produced. Then we have tuning fork. So in tuning fork, you strike one of the prong, then the tuning fork starts vibrating. And here we hear a very feeble sound, but we can see the vibrating tuning fork. If you touch a small ball, a light ball suspended through a thread, suspended from a thread. So then if you touch that with the prong, the ball will start vibrating. Okay, so if a vibrating body is the source of the sound. So what is the source of the sound? Vibrating body. When body vibrates, it produces sound. All the vibrating bodies will produce sound. Okay.
Yes, ma'am.
And we know that sound is a form of energy, and it is mechanical and energy because we energy and kinetic energy into potential energy. And since sound waves are mechanical waves, they require a material medium for propagation. Sound waves cannot travel through vacuum. And this can be proved with the help of a bell jar experiment. So we have a bell jar, we have a bell inside it. This is connected to a vacuum pump and the bell is switched on. So you can hear the bell ringing initially. Now, once it is connected to vacuum pump, we start removing air from it and slowly the vacuum is created and the bell sound becomes feeble, and finally you cannot hear it. Why you cannot hear it? Can anyone tell me?
Ma'am, may I say?
Yes.
Ma'am, because since sound requires medium to travel, if vacuum works, then it will start removing the air from the jar. So basically, when there is no air present, how will it travel
There's no
or
medium.
propagate through?
Yes.
Yes.
There's no medium for propagation, and so we cannot hear the sound. But we can see the bell ringing, but we cannot hear the bell ringing. Why? Because the sound waves are not propagated from the bell to outside air. So we require a material medium for propagation. You all must have played and you must have noticed that if you have an and railing, and if it is a long, like in the staircase, we have the railings. So on the railings, if someone is tapping at the top end and the other person is putting the ear down and he hears a very quick sound, the sound travels fastest in metals. Then the second fast is in liquids and the slowest is in the gases. Now, what are the requisites for the material medium for propagation of sound? This is very, very important. Now, there are three requisites for the material medium to propagate. Now, the first and most important is that in the material medium, the particles should be elastic. What you mean by elastic is that once the particles are displaced, they should be able to come back to their initial position. Okay, so the medium must be elastic so that its particles may come back to their initial position after the displacement on either side. So the first requisite is the elasticity of the medium. The particles of the medium should be elastic. So once they are disturbed, they should come back to their original position, then they can go back. So the medium must have inertia so that its particles can store mechanical energy. Now, this material medium, if it doesn't have inertia, it will not come back to its position and it will not store mechanical energy. So the second most important requisite is the inertia. The particles should have inertia so that once they are displaced, they should be capable of coming back to the original position and then maintain the inertia. So the medium should be frictionless so that no loss of energy in propagation of the sound through it. The medium should be frictionless. So these are the three requisites. Number one, the particles of the medium should be elastic. Number two, the particles should have inertia. That is, they can store the energy. And number three, the medium should be frictionless. So sound can be propagated in solids, liquids, as well as gases. So in solids, the particles are most elastic. And so the sound travels fastest. So sound cannot travel in vacuum. So on moon, there is no medium. And so one cannot hear on moon. So they use walkie-talkie. Light does not require any material medium for propagation because light waves are electromagnetic waves. Please note it down. Light waves are electromagnetic waves. Sound waves are mechanical waves. Mechanical waves require material medium for propagation. Light waves do not require material medium for propagation. Light waves can be propagated in vacuum as well, but sound cannot be transmitted through vacuum. All clear so far?
Yes, ma'am. Light have electromagnetic waves, right?
Light, yeah, light is electromagnetic wave. What about others? Why you have not switched on the camera? So light waves are electromagnetic waves, sound waves are mechanical waves. Now, propagation of sound waves. The sound wave is propagated in two ways. The one is the longitudinal way of propagation, and the other is the transverse medium wave of propagation. So, propagation of sound waves in the medium. So there are two ways by which sound waves are propagated. Number one, that is the longitudinal waves, and number two, that is the transverse waves. Now, what happens when that sound is propagated by longitudinal waves? Longitudinal waves means there is a series of compression and rarefaction. Look at this figure, compression and rarefaction. This metal strip is disturbed, so it is displaced, and so it moves to the point B. So when it moves to the point B, when it moves to this point B, what happens? All the air particles, they are compressed. They are compressed. So there is a compression created. Now, when it goes back to its initial position, then these air particles, they distance themselves, and so there is a rarefaction. Now, again, it goes backwards to the point C, then still there is further rarefaction. Then it comes back to the original position, then again it is moving. So in this way, this compression keeps on moving forward, and then followed by rarefaction. So it is a series of compression and rarefaction. So when the sound waves are propagated with a series of compression and rarefaction, such type of propagation of sound wave is called longitudinal waves formation. So the waves in which the particles of the medium vibrate about their mean position in direction of the propagation of sound are called longitudinal waves. They are called longitudinal waves. So sound waves travel in air in the form of longitudinal waves. Actually, the longitudinal waves can be produced in solids, liquids, and gases as well. So in solids, liquids, and gases, the sound waves are propagated in the form of longitudinal waves. Longitudinal waves consist of a series of compression and rarefaction. Now look at the other picture. Here, if you drop just a pebble, if you drop a pebble into the water, then you see the ripples are formed. And these ripples, they keep moving outward. And if you drop a leaf over any of the ripple, this leaf just goes up and down, down, but the leaf doesn't move outward. The waves are moving outward, but the leaf is going up and down at that point itself. So such type of propagation of sound in which the particles vibrate perpendicular to their propagation, perpendicular to the propagation of the waves, is called transverse waves. Whereas the longitudinal waves are formed when the particles vibrate along with the transmission of the waves. So if waves are formed left and right, the particles will also move left and right. But in longitudinal waves, the waves are going from left to right. The particles will move from top to bottom. That is north and south. Okay. So this is very important. There are two types of wave formation, longitudinal waves and transverse. The wave in which the particles of the medium vibrate about their mean position in the direction perpendicular to the direction of the propagation of wave. Look at page 195, second half, first paragraph. Could you look at the wave in which the particles of the medium vibrate about their mean position?
Yes, ma'am.
Ma'am, you have to
Underline.
mark them. Mark that.
Yes, please mark. Okay, so such waves are transverse waves. Whereas page 194, the wave, last paragraph, the wave in which the particles of the medium vibrate about their mean position in the direction of propagation of sound is called longitudinal wave. Thus, sound waves travel in air in the form of longitudinal waves. So actually, the longitudinal waves can be produced in solids, liquids, as well as gases. So at compression, the density of the and the pressure of the medium is maximum, whereas at rarefaction, the density and the pressure of the medium is minimum. So this entire paragraph is important. The characteristics of the sound waves. So wave is produced by the periodic disturbance at a point of the medium. So it's produced by the periodic disturbance. The disturbance has to be periodic. It should be followed again and again after certain interval of time. So due to the propagation of wave in the medium, the particles of the medium vibrate about their mean position without leaving their position. They are vibrating about their mean position. The energy is transferred with a constant speed from one place of medium to another. So one place of the medium to another, it is the energy is being transmitted, or transferred, but the particles, they just keep vibrating. They keep vibrating. Okay. These are very important characteristics. It is often frequently asked question. Give the characteristics of sound waves. Now some terms related to the wave motion. Amplitude. So when a wave passes through a medium, so amplitude, when a wave passes through a medium, the maximum displacement of the particle on the medium on either side of its mean position is called amplitude. So amplitude A is measured in meter. Unit is meter. So it is the maximum displacement from its mean position to any one of the extreme position. That is called amplitude. Time period, the time taken by a wave of the medium to complete its one vibration is called the time period of it. How much time taken for one vibration? That is the time. So one complete to and fro motion. And it is denoted by capital T, and SI unit is second. The frequency, that is number of vibrations made by the particles of the medium in 1 second, is called frequency of the wave. That is number of waves The frequency and time period are correlated. F is equal to 1 by T. Because T is 1 by F. That is why F is equal to 1 by T. So frequency of a wave is equal to the frequency of vibration of its source. It's a characteristic of its source that produces the disturbance. It does not depend upon the amplitude of the vibration. Frequency is independent of the amplitude. Wavelength. The distance traveled by the wave in 1 second is called wavelength. So the distance traveled by the wave in one time period of the vibration is called wavelength. In 1 second, that is the speed, wave velocity. So wavelength, that is the distance traveled by the wave in one time period of vibration. So in one time period of vibration, whatever is the distance traveled, that is called wavelength. And wave velocity, that is the distance traveled by a wave in 1 second, is called the wave velocity or wave speed. So wave velocity is denoted by capital V. So we have two types of graphs with us. Displacement time graph, in which we have displacement along the y-axis and time along the x-axis. So the distance between two troughs, these are called trough. These are the crest. The upper ones are the crest, the lower one is the trough. So the distance between the two crests, since it is time axis, it is time period. It's the time period. The distance, if we have displacement distance time graph, then the distance between the two crests is called lambda, that is the wavelength, lambda or the wavelength. Quickly go through this part. Quickly go through this part. Any doubts so far?
No, ma'am.
Janvi,
No, ma'am.
Ashi? All clear? Okay.
Yes.
Okay. So we'll move to the next part of it. So we have two types of graphs here. We have displacement distance graph and displacement time graph. Both of the graphs you should draw two types. So amplitude is denoted by small a. Displacement should be in meters and distance should be in meters, whereas time should be in seconds. Okay. Now, relationship between the velocity time graph, wavelength, and frequency. So relationship between wavelength, wave velocity, and frequency. Now, we know the definition. Definition, what is lambda? That is the distance traveled by the wave in one time period. That is in t second. So in t seconds, wave travels lambda meter. So in 1 second, the wave will travel lambda by t seconds, t meters, lambda by t meters, and lambda by t. That means what? 1 by f. T is equal to 1 by f. So see, t seconds, that is wavelength, a time period, wave travels lambda meters. So in 1 second, the wave will travel lambda by t meters. So 1 second, it travels lambda into 1 by t. So it becomes lambda into f, because f is equal to 1 by t. So wave velocity is equal to f lambda, where f stands for frequency and lambda stands for wavelength. Clear? You are asked to derive this, so you should know the derivation. So wave velocity v, small v, is equal to f lambda. So if you know this, you can find out this. Similarly, if you know this, you can find out this. If you know this, you can find out this. Clear?
Yes, ma'am.
Speed of sound in different media. So speed of sound is different in different media. The speed of sound is more in solids, less in liquids, and least in gases. I gave you the reason earlier, because the particles are more elastic in solids than in liquids and then gases. So the speed of sound is nearly 5,100 meter per second in steel, 1,450 meter per second in water, and 330 meter per second in air at 0 degrees Celsius. So you should know all these three values. Mark them. 5100 meter per second in steel, 1450 meter per second in water, and 330 meter per second at 0 degrees Celsius in air. Normally it is 340 at the room temperature. Generally, we take it as 340. So the speed of sound in a medium depends upon two factors. Number one, that is the elasticity of the medium, and number two, the density of the medium. So V is given, it should be small v. V is given under elasticity, under root elasticity upon P. E stands for elasticity. And P, that is rho, it should be rho. Rho stands for the density. You have to just know the formula. You don't have the numericals based on this. So the factors affecting the speed of the sound in gases. This is important. The speed of sound is different in different media. We know that. So in gases, the factors affecting number one is the density. So we have already the relation V is equal to under root
on P.
E upon rho. And here we don't have the elasticity. We have Yang P. This is a different thing. So it is inversely proportional to the square root of density of the gas, and it is directly proportional to the elasticity. So effect of density, since it is inversely proportional to the density, if the density increases, speed decreases. Density increases, speed decreases. Density decreases, speed increases. What is the first factor affecting the speed of the sound in gases?
Ma'am, may I say
Yes.
elasticity of the medium?
The first factor that is affecting the speed of sound in gases is the density. Okay, it is the density. This is what we did just now. So density, speed of the sound is inversely proportional to density. The more is the density of the gas, the less is the speed of the sound. The less is the density of the gas, the more is the speed of the sound. Now, can you tell me, speed of sound will be more in nitrogen or in oxygen? Speed of sound will be more in nitrogen or in oxygen?
Oxygen.
Why? What is the vapor density of oxygen? Anybody knows the vapor density of oxygen? What is the vapor density of oxygen?
8.
Correct. Vapor density of oxygen is 8. And vapor density of nitrogen is 7. Vapor density is half of the molecular mass. Vapor density is half of the molecular mass. Note it there. This is very important. You will require in 10th standard also. So vapor density is half of the molecular mass. Molecular mass, one molecule of gas of oxygen, or one molecule of oxygen gas will measure 16 units. And so vapor density becomes half of 16, that is 8. What is the vapor density of water? Vapor density of water. What is the formula for water? H2O.
H2O.
So hydrogen का mass कितना हो गया? How
0.
much is hydrogen का mass 2 हो गया ना? 2 atomic mass unit. And oxygen का mass कितना हो गया? 16.
16.
So 16 plus 2, 18. 18 divided by 2, 9. Okay. Oxygen का vapor density is 16. Sorry. Oxygen का vapor density is 16 because one molecule of oxygen is 16 plus 16, 32. Okay. So, one molecule of oxygen is 32. 32 ka आधा 16. And what vapor density of water molecule कितना आया? 9. Correct. Please understand this point properly. See, suppose we have this volume. Okay. This is a cuboid. Or here we have oxygen molecules. Okay, let us say this is open. It is open, okay? We have oxygen molecules and this is an open box. Now, if we add moisture to it, so there will be some water molecules also.
Yes, ma'am.
And it's an open box. So jitna water molecules andar gaya, to oxygen molecules bahar nikal gaya. Now, oxygen molecule ka vapor density is 16. Water molecule ka vapor density is 9. Now, what happens? So tell me the vapor density, the average vapor density of dry oxygen and average vapor density of moist oxygen. Kiska jada? Which one will be more? Average density of dry oxygen or average density of moist oxygen?
Ma'am, may I say?
Yes.
The average density of dry oxygen.
Average density of dry oxygen will be more. Average density of moist oxygen will be less. What about others? Are you people sleeping or not interested? Or you're not understanding? Or you just don't want to say anything? So average density of dry air will be more than the average density of moist air. So now tell me the speed of sound when wave velocity in dry air and wave velocity in moist air. Which one will be more? Which one will be more?
Ma'am, may I say?
Yes.
Moisture.
Wave velocity in moist air will be more because velocity is inversely proportional to the vapor density.
Okay.
So lesser is the vapor density, more is the velocity. इसका average vapor density कम हो गया, तो velocity ज्यादा. अभी मुझे बताओ, dry, sunny day and moist, rainy day. speed of sound will be more in which condition? In which condition the speed of sound will be more? Dry, sunny day, moist, rainy day. Yes.
The speed of sound will be more in moist rainy day.
Yes, because vapor density decreases. Moisture is more. Vapor density decreases, the speed increases. समझ में आया जानवी?
Yes, ma'am.
आशी? अच्छा एक बात बताओ, आपने जनरली देखा है कि सर्दी की रात होती है तब साउंड बहुत दूर तक जाता है या गर्मी की रात में साउंड बहुत दूर तक जाता है?
मैम सर्दी के
क्यों?
तो डेंसिटी कम हो जाती है तो फिर
डेंसिटी
तो
कम
फिर
हो जाती है
स्पीड
air की।
बढ़ जाती है द स्पीड ऑफ साउंड इंक्रीजेस ड्यू टू द डिक्रीज
So in cold winter nights, okay, because of the moisture, because of that, the density of air is less, and as a result, the speed of the sound is more. So is the first factor clear, effect of density?
Yes, ma'am.
Now the second one, effect of temperature. Now, when you heat gases, what will happen? Gases will expand or contract? If you heat gases, gases expand or contract?
Expand.
Expand. So when gases expand, the density decreases or increases?
Decreases.
Decreases. And so the volume, the velocity of gas will increase or decrease?
Increase.
Increase. Exactly. So this is what is the effect of temperature. If the temperature increases, the speed of the sound in a gas increases with the increase in temperature. Reason that with the increase in temperature, the density decreases and consequently the speed of the sound increases. समझ में आई बात? It is related to density only. So velocity of the gas is directly proportional to the square root of temperature. And it is found out that Vt at any temperature T, velocity will be velocity at 0 degree plus 0.61 into the rise in temperature. Suppose it is 330 meter per second at 0 degrees Celsius. So at 40 degrees Celsius, how much will be the velocity? So 330 plus 40 into 0.6. Calculate. 330 plus 40 into 0.6. So how much is the speed of the gas? Speed of the sound. Sorry.
मैम 330 into 40
330 into 40. 330 plus 40 into 0.6. How much do you get? How long you will take to do the small calculation?
I'm 354.
मैम I also got answer
How much? 354 meter per second.
meter per second.
So as the speed of the temperature of air increases, the speed of the sound increases. clear and you can calculate. So the density, now effect of humidity. The speed of the sound in air increases with the increase in humidity. I told you that the density of water vapor is 5 by 8 times the density of the dry air. And so the density decreases and speed of the sound increases. The effect of direction, the speed of the sound increases or decreases according to the direction of the wind. If it is propagated in the direction of the wind, then the speed increases. In opposite direction of the direction of the wind, the velocity decreases. Towards the direction increases, against the direction of the wind decreases. So the speed of a distant music is quickly and loudly heard if it is coming with the wind. On the other hand, it is difficult to hear if the wind blows in opposite direction. Now, factors which are not affecting the speed of the sound. Number one, these are also very, very important. Number one, there is the pressure. Now, the P by rho ratio remains unchanged with the pressure. अगर आप pressure increase करोगे, density of the gases increase. You increase the pressure, the density of the gas increases. So P by rho ratio does not, the P by rho ratio does not change. So that is why the speed of the sound in gas is independent of the pressure. It is independent of the effect of altitude. And it is independent of the wavelength. It does not depend upon the wavelength or the frequency. So these are the three factors which do not affect the speed of the sound. Number one, independent of pressure, because P by rho ratio remains unchanged. As the pressure increases, density also increases, and P by rho ratio remains unchanged. Then the effect of the amplitude, it is independent of the effect of the amplitude and wavelength. Now, comparison of speed of sound with light. So as we have already discussed, the light can travel through vacuum, sound cannot travel through vacuum, because light waves are electromagnetic waves. And the speed of the electromagnetic wave is 3 into 10 raised to power 8 meter per second, whereas the speed of the light wave is 330 meter per second at 0 degrees Celsius. So the light waves can travel in vacuum, sound waves cannot travel in vacuum. Speed of the light waves is much, much higher than the speed of the sound waves. And this is the reason why we hear the thunderbolt, later we see the lightning first. So they both are happening simultaneously, lightning and the thunderbolt. But since the speed of the sound is lesser than the speed of the light, we hear the lightning, we see the lightning first, and then we hear the thunderbolt. Similarly, if you're watching a match, cricket match, you see the batsman moving the bat first and you hear the tuck sound later. So because the speed of the sound is much, much less than the speed of the light. The speed of light waves decrease in optically denser medium, whereas the speed of sound wave is more in solids, less in liquid, and least in gases. The light waves are transverse electromagnetic waves, whereas sound waves are longitudinal mechanical waves. So these are the differences and very, very important. And consequences of large difference of the sound waves and light waves, we have discussed, thunder and lightning, then spectators wala, and when the athletes during the starter point, so the athletes are told to see the smoke, not hear the sound. So they should be looking at the smoke. Once they see the smoke, they should start running. So the spectators sitting at the distance hear the sound of the fire a little later, while the smoke is instantaneously seen. The reason that the velocity of light is much, much more than the velocity of sound. The experimental determination of speed of sound in air. How do we determine the speed of the sound in air? That is, we choose two places at high altitude, A and B facing each other. So from point A, the sound, the person fires the gun, and in point B, the person has a stopwatch. When he hears the sound, he will stop it. So in with this way, you get you know the distance, you know the time taken, and so you take 2, 3 readings like that and take the average of it. So velocity is equal to distance upon time. So we measure the 2 time intervals 2 times, first for the sound to travel, and then for the elimination due to the wind. So we take 2, 3. However, the speed of the sound so determined is not very accurate because of the personal error. But we take it as velocity is equal to distance upon time. Okay. Quickly, 2 minutes ka break. Go through whatever part we have done. And if you have any doubt, you can ask me now itself. So, any doubts?
No, ma'am.
So let us do the numericals. Everybody switch on the camera. Can we first one? Human heart beats 75 times 1 minute. So what is the frequency? Frequency is number of beats per second. How many seconds are there in 1 minute, Janvi?
Ma'am, could you repeat your question?
Numerical, page 203, question number 1. How will we do that? How will we do this, Janvi?
Frequency is equals to 1 upon the time period.
75 beats in 60 seconds. And frequency is equal to number of beats in 1 second. So 60 seconds, 75 beats, 1 second, 75 upon 60. How much do we get? So
Ma'am,
F 1.25 volts and time period is equal to 1 by F. So that is equal to 4 upon 5. That is equal to 0.8 second. 0.8 second. Is this clear to everyone?
Yes, ma'am.
Next question. Time period of a simple pendulum is 2 seconds. T is given 2 seconds. What is frequency? Quick.
Ma'am, F is equals to
Can I say?
20.
Yes, yeah.
Ma'am, frequency will be 1 upon 2 is equal to 0.5 hertz.
Correct. Question number 3, Ashi. The separation between two consecutive crests. So separation between two consecutive crests is lambda. Is 100 meters. So lambda is given 100 meters. That is wavelength is given 100 meters. Wave velocity is given. Wave velocity is given 20 meter per second. So find frequency. What's the formula? What's the formula?
V lambda is equals to V into
P equals to
V is equals to F into V.
F into lambda.
Sorry, F into lambda.
And so you have V, you have F. So lambda is equal to V upon F. So 20 upon 100. So find out quickly. Oh, you have to find? Sorry, you have to
No,
find?
but we don't have frequency, right?
Yes.
Then lambda upon V will come.
V upon lambda is equal to F.
Yes, ma'am, I've gotten
Ayan.
the answer.
Understood. Question number 4, Ayan. What all things are given to us?
Yes.
Read the question loudly.
Ma'am, a longitudinal wave travels at speed of 0.3 meter per second. And the frequency of wave is 20 hertz.
So what is given to us? What is given to us?
Ma'am, the speed is given.
So velocity is given to us 0.3 meter s minus 1.
And the frequency of the wave.
Frequency is given. So we have to find. What do we have to find? We have to find lambda. Quickly find.
Ma'am, 0.015 meter.
Correct. Are these all clear to you people?
Yes, ma'am.
Yes.
So remaining questions will be your homework, which I will do tomorrow. Now let us move to the last part. Very simple part. So infrasonic, ultrasonic, I have already told you what are infrasonic waves, less than 20 hertz, whose frequency is less than 20 hertz and our ears cannot see. They are called infrasonic, and about 20,000 hertz, it is called ultrasonic. Children can hear the sound of somewhat high frequencies, say up to 30 hertz. Old people can hear the sound only up to a frequency of 12 kilohertz. That is 12,000 hertz. Human ear is most sensitive at a range of 2,000 hertz to 3,000 hertz. So where we can hear even a feeble sound. So that's the most compatible hearing or audible range. So the sound of frequency of range 20 hertz to 20,000 hertz is called sonic or audible sound. And below that, it is called infrasonic, and above that is called ultrasonic. Animals can produce and hear the sound of frequency below 20 hertz. Elephants and whales produce infrasonic sound waves less than 20 hertz. Fishes can hear sound waves of frequency range between 1 to 25 hertz. Some animals produce ultrasonic sounds and communicate through them. Dog can hear the frequency up to 50 hertz. Bats up to 1000 kilohertz. Dolphins up to the higher frequency up to 150 kilohertz. Ultrasonic, we know that these are the wave sounds which are about 20,000 hertz and they travel with the speed similar to the audible sound travels. So properties of ultrasonic sound has all the properties similar to the ordinary sound, but because of the high frequency, this is very, very important. Because of the high frequency, ultrasonic sound has following two additional properties. The energy carried by ultrasonic is very high, and the ultrasonic sound can travel along a well-defined straight line path. It does not bend appreciably at edges. So these are the two properties. Number one, they're highly energetic. Number two, they have high definition of the path. So they travel along a well-defined path. So because of these two properties, they found the application in ultrasound. So application of ultrasound, so bats avoid obstacles because they produce ultrasonic waves, and these waves go and strike the obstacles and come back to them, and then they can judge the distance. Ultrasound is used for drilling holes or making cuts of the desired shape in glass. For cleaning minute objects such as a parts of water, electronic components, ultrasound is used. And then the objects are placed in the cleaning solution. Then you just pass the ultrasound waves and you get almost objects. For detection of defects in the metals, ultrasound is used. Ultrasound passes through the objects if there is no defect. If there is a defect, the sound gets back. Ultrasonography, that is also where ultrasound is used. Electrocardiography, then it is used in surgery to remove cataract, and then it is used sonar. It is used to detect the distance of the object from the under the water. Sound, navigation, and ranging. Sonar. Distance between ultrasonic and supersonic. Now, ultrasonic, that is about 20,000 hertz. That is ultrasonic. Supersonic are those objects which produce sound greater than the objects produces the ultrasonic and supersonic. So ultrasonic, these are the sound waves of higher frequencies, more than 20 kilohertz. Whereas supersonic, the sound with greater than the speed of the sound. Okay, supersonic are the objects which travel with a speed greater than the speed of the sound. So ultrasonic and supersonic are two different things. This is very, very important. Mark this paragraph. So if a body is traveling at a speed higher than the speed of the sound, so then it is called supersonic jet or something like that. So Concorde jets and fighter planes. So with this, we end the chapter. So what you have to do is that question answers, mark everything, and also the numericals. Okay. Clear?
Yes, ma'am.
Okay, so Quickly, we'll have 10 minutes of break and then we'll start chemistry, periodic table. Let us start. Okay. Chemistry, periodic table. Where is Ayan?